In the previous video, we covered the two-slit interference. Let's now take a look at single-slit diffraction as well as the diffraction grating. In the double-slit or two-slit interference, we have light that is incident upon a double slit and an interference pattern of bright fringes and dark fringes are formed on the screen a distance x from the double slit. If we replace the double slit with a single slit, the slit has a width of A. So light is incident upon the single slit. Due to the diffraction of light, light will expand out into the space behind the single slit. And due to the Huygens principle, each point on the space on the slit, each point on the slit rather, may be considered as a light source. So much so that you have multiple light sources that will be interfering on the screen. You have multiple light waves that will be incident on the screen, that will be overlapping on the screen, and a diffraction pattern will be formed on the screen. A diffraction pattern of alternating maxima and minima will be formed on the screen. The minima, the locations of the minima on the screen are given by the following equations. A sine theta is equal to m lambda and y sub m is equal to mx lambda over A. A again is the width of the slit width. And m is equal to plus minus 1, plus minus 2, plus minus 3, plus minus 4, and so on. For the locations of the maxima, for the bright fringes, the central maximum, y central maximum will be 0, meaning it's located at the center or what could be considered as the center of the diffraction pattern. It will be located along the center line from the middle of the slit to the screen. The other maximum locations, the other locations of the bright fringes is given by y maximum is equal to ym plus ym plus 1 minus ym over 2, where ym is the location of the minima, meaning it's with respect to the minima. So ym here, so if it's y1, so y1 plus 1 minus y1 divided by 2. On the other hand, if we replace the double slit with a diffraction grating, a diffraction grating is basically a barrier that has multiple slits. A diffraction pattern will also be formed on the screen. For the locations of the maxima on the screen, you have the following equations. D sine theta is equal to m lambda. Y sub m is equal to mx lambda over d, where m is equal to 0, 1, 2, 3, and so on. And then you also have delta theta hw is equal to lambda over nd cosine theta. M is equal to 0, 1, 2, 3, 4, 5, and so on is referred to as the order number. M is equal to 0 is the zeroth order line or the central maximum. M is equal to 1 is called the first order line. It doesn't matter whether it is on this side or on the other side of the screen. M is equal to 0, M is equal to 1, M is equal to 2, and so on. M is equal to 1 is referred to as the first order line. M is equal to 2 is referred to as the second order line. M is equal to 3 is the third order line, and so on. D is the slit to slit distance. So you have multiple slits. From one slit to the other, the distance between the middle of one slit to the middle of the next slit is the slit to slit distance D. Delta HW is referred to as the half width of the line. So if you look at the bright fringe, half of that bright fringe is the half width. Half of that bright fringe is delta theta HW. And capital N is the number of slits in the grating. So if there are 100 slits in the grating, N is equal to 100. And so on. The diffraction grating is very good at distinguishing the lines of light with very close values of wavelength. So if, for instance, if two beams of light are incident on the grating, so you have lambda 1 and then lambda 2, the diffraction grating, in terms of the diffraction pattern, the resulting diffraction pattern, the diffraction grating is very good in distinguishing the pattern of one light from the pattern of the other light, particularly if the wavelengths are very close in values. With the single slit diffraction and even with the two slit interference, they're not very good in distinguishing wavelengths with very close values. Whereas the diffraction grating is very good at distinguishing wavelengths of very close values. We have the dispersion D is equal to M over D cosine theta is equal to delta theta over delta lambda. Capital R is equal to NM is equal to lambda average divided by delta lambda. The dispersion D unit, radians per meter, or in some cases, degree per meter. The dispersion refers to the separation between the lines of light 1 and light 2. And delta theta is the angle difference between the lines of light 1 and light 2, between the angular location of the lines of light 1 and the angular location of the lines of light 2. Delta lambda is the difference between the wavelengths, whereas lambda average is the average of the two wavelengths. So that's it for now. In the next video, we'll take a look at examples part of what we have covered in terms of the interference and diffraction of light. So thank you for watching.